hit the record button, which I've done. Okay, so let me hand it over to group one.
All right, perfect. Thank you so much, Dr. Chong. So just to introduce everyone, thank you all for coming. This is Team 1's final presentation on the solar Ray-tor, a small-scale heliostat for industrial solar processing. My name is Jose Rivas, and here are my teammates, Mohammed Al-Shabu, Natalie Broyd, Antonella Cipriani, Evan Lynch, Samuel Paris, and Max Roval. Move on to the next slide. Here you guys can see the presentation outline that we'll be going through today. We'll start off with the Hedgehog concept, then the product overview, the analysis for our mirror, frame, and control system, some key features of our design, the cost analysis per module, reasons why you should prototype the solar Ray-tor, and we'll end it off with the conclusion and acknowledgement. So to introduce you to our design, the solar Ray-tor is a module consisting of 4 individually controlled heliostats with a total of 1 meter squared of reflective area. The concept aims to tackle the high costs associated with classical heliostat designs, which employ large steel structures and multiple drive systems. The next slide. Our Hedgehog concept is shown below, which is the solar Ray-tor is a modular industrial solar processing unit designed for linear expansion. Our design is modular because most of our parts are OTS, which reduces manufacturing time and overall costs. We also reduce the number of screws by using an epoxy adhesive to hold some of the components together. These will be shown more in detail in slides to come. Our design can also be linear expanded because each heliostat has its own control system and frame structure, meaning that we should be able to make a module with any number of heliostats if needed. Next page. So we decided to split our design into 3 subsystems: the mirror, which consists of the standard glass mirror, the frame, which consists of the galvanized steel pipe, the control system, which consists of 2 servo motors, the Arduino Nano, the AC-DC converter, the bracket, and the adapter. The overall dimensions of the module is 2.3 meters by 0.9 meters by 0.3 meters. Thank you, and I'll pass it on to Antonella for the mirror analysis.
So the mirrors that we use in our subsystem are standard flat glass mirrors. The total reflective area per module is 1 meter squared. There are 4 total mirrors, each having 500 millimeters by 500 millimeters with a 3 millimeter thickness, and they are mounted onto the bracket mount using an epoxy adhesive with resin. Next slide, please. The following customer needs were mapped to the mirror subsystem to determine how the solar Ray-tor met them. According to the customer, the total collection area must be at least 1 meter squared. The solar Ray-tor has a 1 meter squared reflective surface. The optical losses due to tracking error must not exceed 40%, and the average yearly optical losses for our design was found to be 29%. The individual heliostats within module units cannot shade other heliostats in that unit. Our trapezoidal configuration eliminates shading and blocking losses. The cost must also be below $100 per meter squared. The mirror subsystem cost totals to $3 for 1 meter squared of reflective surface. Individual parts must be equal in price or less expensive than the closest available OTS part. Each mirror in the module is purchased off the shelf. The reflecting surface must also be washable, able to withstand high pressure cleaning sprays above 500 psi. Each mirror has a compressive strength of 145 kpsi. The focal thermal power input to the receiver must be at least 1 megawatt. The power generation for our proposed field layout was found to be 1.73 megawatts. Finally, the solar concentration ratio must be at least 1,000 suns. The proposed field layout provides a solar concentration ratio of 1,265 suns. Next slide, please. So, to talk about our field layout, a radial-staggered pattern is employed to determine the spacing of the modules in relation to each other in the field layout. Studies have shown this pattern to be most efficient for a given land area because it cuts down on shading and blocking losses. The pattern is defined by the radial and azimuthal spacing between modules. There will be 3 zones in the field, as you can see in the layout in the slide, and each zone is represented by each color in the figure. The azimuth angular spacing is constant within a zone, while the radial spacing for all zones is the same, 1.47 meters. The first zone consists of one row with 10 heliostats. As you can see from the table, the radial and azimuthal spacing results in a total of 350 modules in the field. Next slide, please. So the optical efficiency measures the energy loss of the proposed field layout, and it can be determined by considering the attenuation efficiency, the mirror reflectivity, the shadowing and the blocking efficiency, and the cosine efficiency. The mirror reflectivity is taken to be 95%, while the shadowing and blocking loss is taken to be 5.6%. The attenuation efficiency is a product of the distance between the heliostat and receiver and is calculated for all 350 modules in the field. The most significant contributor to loss, the cosine efficiency, is due to the angle of incidence between sunlight and a vector normal to each heliostat. Thus, the average yearly optical efficiency of all 350 modules was found to be 71%, which exceeds the customer need that optical losses must be less than 40%. Next slide, please. So the focal thermal power input to the receiver is a product of the area of each heliostat, the optical efficiency, and the direct normal irradiance. In a real CSP plant, the heliostats begin working when the solar altitude angle, alpha, is higher than 15 degrees and the DNI is higher than 150 watts per meter squared. The focal thermal power input to the receiver is thus summed over the days in the year when these constraints are met for every heliostat in the field. An assumed incident solar irradiance of 1000 watts per meter squared is assumed, with the incidence angle dependent on the location of each heliostat in the field. Thus, the total power generation for the proposed field layout is 1.73 megawatts, and this was found to exceed the customer need of 1 megawatt. Next slide, please. Finally, we want to talk about the solar concentration ratio of our field, which is given as the ratio of the total reflective area to the area of the receiver, while also accounting for the optical efficiency of our layout. So the total reflective area for 350 modules is 350 meters squared, since there are 4 mirrors in one module, while the receiver aperture diameter is assumed to be 0.5 meters. Thus, the optical efficiency was calculated as previously to be 71%, and the solar concentration ratio is found to be 1,265 suns, which also exceeds the customer need of at least 1,000 suns. Next slide, please.
Each heliostat is supported by a 0.5 meter long galvanized steel pipe that is buried 0.33 meters into the ground, creating a moment to counteract tipping. There's a hole at the bottom of the pipe where the central power wires run up through the hollow pipe into the adapter to reach the control subsystem. Galvanized steel is a zinc-coated carbon steel which provides corrosion resistance. It is utilized within the design due to its strength, ability to withstand outdoor conditions for over 20 years, and cost efficiency. Next slide, please. An ABS plastic adapter mounts onto each pipe and connects the mirror and controls assemblies to the frame using an epoxy adhesive. It includes an enclosure for housing the azimuth servo motor, an enclosure for housing the microcontroller and AC to DC converter, mounting holes for self-tapping screws into the ABS, and an opening that allows for the lid to be screwed into the ABS, making the controls components easily accessible while protecting them. Both ABS plastic components are 2 out of 3 custom parts in the design and are manufactured via 3D printing. We considered injection molding, but tooling costs were significant. ABS plastic was chosen because of its strong resistance to corrosion, cost efficiency, and because it's easy to machine. Next slide, please. The following customer needs were mapped to the frame subsystem to determine how the solar Ray-tor met them. According to the customer, each module must be composed of 2 to 16 heliostats. The solar Ray-tor consists of 4 heliostats. The cost must be below $100 per meter squared. For our design, the total frame cost per module is $30.20. The total reflecting area to module area should be significant, at least 50%, which is meant by the solar Ray-tor. The operational lifetime of the installation must exceed 20 years. This lifetime is met due to the material selection within the subsystem. The system must also operate under the ambient and solar conditions in Las Vegas, capable of withstanding winds up to 90 miles per hour. The solar Ray-tor can withstand 120 miles per hour in its protective stow configuration. Lastly, the topography of the overall installation is completely flat. The pedestal is staked 0.33 meters to provide adequate support to prevent deflection of the pedestal. Next slide, please. The total bending stress generated on the pipe is composed of wind and mirror weight compressive stresses. The diagram summarizes the forces and moments acting on the pedestal. When the wind blows asymmetrically onto the pipe, a moment in the azimuth direction occurs. Thus, there's also a torsional stress induced on the pipe. The combined stress in different directions is given by the second equation. Because the combined stress of 2.67 megapascals is less than the material yield strength of 470 megapascals, it is assumed that the pipe is safe from wind loads. Next slide, please. We also analyze the adhesive strength versus the wind pressure created by drafts entering the opening on the shaft. Air was treated as a fluid, and the following assumptions were made: two-dimensional flow, incompressible flow, steady flow, fully developed flow, and no slip at the boundary wall. Noting the flow is steady and incompressible, Bernoulli's equation for 2 points can be applied to the system to find the pressure acting on the plastic adapter. The inlet at the side of the shaft will be labeled as 0.1, and the cross-sectional area of the plastic adapter at the top of the shaft will be 0.2. The strongest reported wind speed in Las Vegas was 90 miles per hour, or 40 meters per second. This is the maximum velocity of the wind, V1. Knowing that the speed of the wind is the only input to the system, all other variables can be removed, yielding the top equation, where P2 is the pressure acting on the adapter. Assuming atmospheric pressure at the inlet and an ambient temperature of 85 degrees Fahrenheit, the density of air was determined to be 1.167 kilograms per meter cubed. The distance from the inlet to the top of the pipe was measured to be 0.15 meters, and the gravitational constant G is 9.81 meters per second squared. This results in a pressure of 0.182 kilopascals. The adhesive strength of epoxy was rated at 54 megapascals, and the total weight of the components above the pipe was found to be 2.22 kilograms, resulting in a pressure of 0.11 kilopascals, which is negligible relative to the tensile strength of epoxy. Therefore, the pressure exerted on the mirror was endured by the tensile strength of the epoxy adhesive in addition to the weight of components above the pipe. Next slide, please.
Thank you, Natalie. We will now discuss the control subsystem. The control subsystem is defined as the components that provide motion and logic to our product. There are 5 major components to our control system, and all of them are off the shelf. These components are the pan and tilt mount, the MG945 servo motor, the MG946R servo motor, a microcontroller, and AC/DC converter. The pan and tilt kit is composed of brackets, fasteners, sealed ball bearings, and servo adapters. These brackets are made of stamped aluminum and anodized black to ensure corrosion resistance. Furthermore, the aluminum reduces the overall rotational mass, reducing power consumption and internal servo motor wear. All fasteners included in this kit are zinc coated to ensure corrosion resistance. A bearing is incorporated to the non-driven side of the bracket to provide support and reduce friction. This bearing is internally lubricated and externally sealed. The aluminum servo adapters transmit power from the servo motor to the brackets. They are anodized clear to increase corrosion resistance. The next component is the MG945 servo motor. This servo has 180 degrees of travel and uses an internal closed feedback loop to determine its position. The case is made of ABS plastic and is completely sealed. Internally, there is metal gears that ensures accuracy and reliability. The stall current of the servo is 1.2 amps at 6 volts. The next component is the MG946R servo motor. This servo has 360 degrees of travel and also uses an internal closed feedback loop. The case is also made of ABS plastic and completely sealed. The stall current of this servo is 1.1 amps at 6 volts. The next component is the microcontroller, which is similar in size to an Arduino Nano. This controller receives open loop main control signals from the central computer. The trajectory of the sun will be uploaded to each individual heliostat, and the program will take into account the location of the individual heliostat to determine mirror orientation. This controller does not have a dedicated motor controller. Thus, the servos must be powered in conjunction with the AC-DC converter. The microcontroller will only be responsible for generating pulse width modulation signals for the servo. This particular microcontroller has a low power consumption at less than 0.5 watts. The last component of the control subsystem is the AC-DC converter. This is needed to convert standard 120 volt AC voltage to 6 volts for the solarator. Next slide, please. Needs mapping was used to determine how the solarator achieved the customer needs. The first column represents the category of the quantification metric. The second represents the corresponding customer need, and the final column represents the final results of our product. Each individual member completed a trade study, and it was found that we valued cost, off-the-shelf part ratio, and individual computer tracking the highest. The customer defined a solar tracking error of less than or equal to 0.5 degrees. This was achieved with an accuracy of less than 0.5 degrees. The customer defined a max receiver height of 100 meters. The solarator is designed to work with a minimum tower height of 3 meters and maximum tower height of 100. The customer defined a max module cost of $100 per meter squared. The control system of our product cost $46.16. The customer requested solar tracking of the module was completely automated. Our product exceeds this as each individual heliostat is independently controlled. The customer requested as many off-the-shelf parts as possible. This control subsystem meets this by being completely off the shelf. Finally, the customer wanted light dispersion to be minimized at the furthest distance. This was achieved up to 100 meters radially from the central tower. Next slide, please. The internal temperature of the housing was calculated to ensure that onboard components would not overheat. This calculation was performed using manufacturer-defined specifications and Ohm's law. The power consumption of the electronics was found by multiplying the current and voltage. This assumed that the servos were stalled and that the power output from the converter was maxed. It was found to be 3.24 watts of thermal load. We then calculated the average wall thickness average thermal conductivity, and use SolidWorks to find the external surface area exposed to convection. The final result was a 14-degree Fahrenheit rise over the ambient temperature. Las Vegas recently had a record temperature of 118 degrees Fahrenheit. This would result in an internal temperature of 132 degrees. The Arduino has the lowest max operating temperature of all components at 160 degrees. Thus, the Solarator would be able to operate in the Nevada desert. Next slide.
Thank you, Evan. The second analysis of the control subsystem will check for possible buckling of the U bracket, shown in the figure on the slide. Treating either side of the bracket as columns, the normal stress produced by the weight of the mirror on the top face of the mid-link servo bracket becomes an axial load through the material. Knowing that the load is supported at either end, it can be assumed that the force that results in the axial load in each panel is half of the weight of the mirror subassembly. The load on each panel was found to be 0.258 megapascals. The side panels of the bracket can be assumed to be fixed at both ends. With this end condition, the critical load due to buckling is found to be 642 kilonewtons. Compared to the load value of 10.8 newtons, the critical load was significantly higher than the maximum load, and therefore it can be determined that the product will not fail due to buckling. Further detailed calculations of this analysis are included in the appendix. The next analysis addresses stress concentration on the side panels to determine the max stress created around the holes. For the nominal stress around the hole calculation, the force applied to the bar can be substituted by half of the weight of the mirror subassembly calculated previously. The rest of the variables were found by measuring the width of the cross-sectional area W, the diameter of the hole D, and the thickness of the bracket T. These values, along with the stress concentration factor, are tabulated in the appendix. This stress can be compared to the yield stress of the bracket to determine whether the material will fail around the holes. The yield strength of aluminum is 276 megapascals. The calculated stress concentration factor was found to be 2.32. The nominal stress around the hole was then found to be 0.379 megapascals, which resulted in a maximum stress of 0.879 megapascals. Compared to the yield strength of 276 megapascals, it can be safely assumed the bracket will not fail around the holes. The final controls analysis performed was to determine the maximum torque experienced by the motor. The U-shaped bracket in the controls assembly can be treated as a moment arm and the mirror as a point mass at the end of that arm. Assuming the worst case scenario, where the mirror is perpendicular to the floor, the maximum torque produced by the mirror assembly on the motor was found to be 1.14 Newton meters, which translates to about 11.6 kilograms per centimeter. The highest rated torque of the motor is 13 kilograms per centimeter, producing a factor of safety of 1.24. Addressing the key features of our product, our first key feature is the stow mode. When the mirror position will be exactly horizontal, ideally parallel to the ground. The heliostat will enter the stowing position when encountering inclement weather and wind speeds over 20 miles per hour. Engaging in the stowing position ensures minimal damage to the mirrors and prevents falling objects from interfering with the control system underneath. Our next key feature addresses the field layout of our product. Individual assemblies within the module will be placed in a trapezoidal configuration to eliminate shadowing and blocking losses. In the field, modules will be placed in a radial-staggered pattern to prevent mechanical interference and minimize shadowing and blocking losses. To meet the power requirement, 350 modules in a radial-staggered pattern will be necessary, with the furthest heliostat distance being 19.62 meters. Our final key feature details the OTS ratio of parts within each module. As in accordance with our Hedgehog concept and shown in the figure on the slide, keeping this ratio at 2 OTS parts to 1 non-OTS part allows for our concept to remain simple in both assembly and in future repairs. Furthermore, as these parts are shipped complete, costs associated with manufacturing are reduced.
Thank you, Samuel. The total cost for one module incorporates off-the-shelf raw material, manufacturing, and assembly costs. Since most of the components were off the shelf, there are only 3 components that needed to be manufactured in one heliostat. Thus, we were able to reduce the manufacturing time, resulting in a reduction of manufacturing costs. Assembly time was implemented to determine the assembly cost. Thus, the total cost for one module is $96.59, which satisfies the customer need.
Thank you, Moxa. So now we're going to go over some reasons why to prototype the solar radiator. The solar radiator's module design reduces manufacturing time and cost, as mentioned before, because most of the parts are OTS. The design has ease of installation and low labor intensity due to the pedestal being staked into the field and the parts being easily assembled. All the electronics are easily accessible for maintenance while also being protected from the weather conditions, such as wind, rain, hail. I'm going to pass it on to Mohammed for the rest of them.
Thank you, Jose. So the U configuration of each module eliminates the shadowing and the blocking losses. The U shape will be facing the tower, so having the heliostats in a line as viewed from the front makes it clear that they cannot shade each other. The radial staggered pattern for the field layout mitigates the shading losses. Having the radial pattern minimizes the portion of the field that will be blocked by the tower's shading at any one time of the day. The field layout minimizes the land area required. The closest packing of modules to the tower is the layout that we have currently. The layout still ensures that the project exceeds the power and optical efficiency demanded by the customer. Each heliostat is a module is individually controlled. This limits the failure of any limiters to one structure in the field. With each heliostat being directly connected to the central hub, defaults in performance will be immediately detected. Next slide, please. So the novelty of the solar Ray-tor lies in its modularity. This means that you can expand the layout field until light dispersion due to large distances makes further expansion non-profitable. So each heliostat is fully independent of one another. So basically the central control hub has full control over each single heliostat. This also results in easier maintenance. So for example, if heliostats were linked by some different contraption, then you risk losing functionality in multiple heliostats at once. The module maximizes the number of heliostats in a single unit with respect to cost. It also eliminates shadowing and blocking losses, and it's easily scalable to produce a field pattern. To conclude, the proposed field layout achieves 1.73 megawatts of power input to the receiver and has an optical efficiency of 0.71. This proves that the design does indeed satisfy all the customer needs quite nicely. Thank you very much. For acknowledgements, we would like to thank the UF Renewable Energy Conversion Laboratory, Dr. Shefe, Dr. Greenslit, Dr. Tranum, Dr. Matthew Trom, and Learning Assistant Devanji Guakward, Northrop Grumman, Cumans, and Carrier for their support for this project. The floor is now open for any questions. Thank you very much.
All right, great. That was 29 minutes. So we've got a little more than 16 minutes for questions from the panel. Tom, you're up.
Oh, okay. Yeah, I know. I'm traditional. I always feel like I should give somebody else a chance to step in. But what the heck? Okay, so I've picked on a number of similar issues with other teams, and I gave Dr. Trom some feedback that covered, just in general terms, a lot of what I've seen here. So I'll try to ask maybe a few new questions. your customer need statement was for what, 1 megawatt of power? Is that correct?
Yes.
Yes.
How much, what percentage of the day would you be able to meet that, and what do they require? Right, as the sun is moving throughout the day, are you meeting 1 megawatt over, from the hours of 9 a.m. to 3 p.m. or what portion of the day do you meet that?
Yes, so the power generation that we talked about was for all days in the year that meet the constraint of having a direct solar radiance greater than 150 watts per meter squared and the solar altitude angle being greater than 15 degrees, because we based it off existing CSP plans.
Okay, so when the sun is 15 degrees above the horizon to when it drops to 15 degrees above the other horizon, that's when you're capable of meeting that customer need?
Yes.
Okay. When you did your analysis of your adhesive, it seemed like you're considering wind blowing into like the hole in the pipe that wires are passing through, and that pressurizing the inside of the pipe and popping the cap off. Is that correct?
Yes.
What's going to happen with say asymmetric wind loading on the mirror? Is that going to load the adhesive at all?
It was not something we considered when doing that calculation. It would be something we
seems
had to
like-
consider for
It
further
seems like. So let's talk more about asymmetric wind loading, right? So you've got asymmetric wind loading on the mirror, because I'm imagining, this system is right behind one in front of it, and as the wind's blowing towards it, you're gonna sort of block the bottom, whatever, half, 2/3, whatever, of the mirror, and you're gonna have a higher wind loading impinging on the top of this thing, right? So when it does that, what is that gonna do to the structure? Is that potentially going to pop the mirror off of your bracket? Is that going to overload the servo that you have to actuate? What's going to happen?
Well, it should not pop it off, only because the tensile strength is so high of the epoxy, and we counteracted tipping of the module by placing more of the pipe underground than above to create a greater moment below.
I'm not so worried about the pipe itself. I'm worried about the attachment of the mirror to that little U bracket that you had.
Oh, I understand.
Yeah, that's a structurally inefficient design, right? You've got essentially a point to counteract a moment, and that points don't like to counteract moments. So I would suggest considering whether that is going to be strong enough. And then you've got, from that point, now you're back through that U bracket to that first servo, right? And that first servo is going to have to react that load, right? It's going to have to create a moment to react that load. And then, back from there is probably a little more structurally robust, but I'd be concerned about those two links. Let's see, what else? I haven't really talked about compliance of structure with anybody, but what is your customer's requirement for you to aim a beam of light at this tower, right? If your structure starts to wobble or starts to deflect, or particularly if your mirror, and I guess you guys have a glass mirror which should be fairly stiff, if that starts to potentially curve at all and it's no longer reflecting light back to the tower, is that going to be a problem? Have you looked at compliance in your system and how that affects efficiency of collection?
Well, all our materials were rated for a 20-year operational lifetime, and we assumed that from this operational lifetime, all materials would then be able to meet the requirements and not exceed the optical losses, which ours are about 29%, and tracking losses of below 0.4 degrees. Past this
it's
20
kind of
year.
the tracking losses that I think are the bigger concern, right? And if you tell me your mirror is going to last in the desert outside for 20 years and it's not going to get scratched and it's not going to, that's fine. I guess I can buy that. What I'm thinking more is, you got to point this thing at the tower, right? Within, I guess your customer says half a degree of angular tolerance. I'm not sure how that plays with, mirrors being closer to a tower versus farther away, but, if you take that for what it is, under wind loading, under really, I guess, wind loading is the major thing here. Under that wind loading, are you going to be able to maintain your pointing at the tower, and is it going to potentially deflect your system so that it disperses that reflection, right? So instead of being a flat surface that's reflecting back in one direction, if it starts to curve, and now you have like a parabola that is reflecting in lots of directions, much of which isn't towards your tower.
Correct. Well, for us, for winds up to 20 miles per hour, we can assume that our product will be able to redirect light to the solar tower. And
Based on what?
Based on the calculation, if I can go to the slide. Based on the wind pressure calculation done for the frame here.
Did you do a deflection analysis here?
Yes. This would be the deflection as of the
that
beam.
Include deflection of the system above the post? Because this looks like a post, which is pretty robust, but I'm concerned about the rest of your system.
No, actually, I don't believe so. That'll be something
Okay.
we'd have to reconsider and calculate.
Okay.
I mean,
I will say.
Yeah.
Go ahead.
Yeah. So one way, like we kind of thought about it, was that we saw that the mirrors, as you said, are pretty stiff. So at some point, their deflection would result in them cracking or breaking, and that's what we assessed. We assessed like what are the wind loads that are going to lead to the system itself or the mirror itself failing, and we didn't include like them bending because we assumed because they're stiff, when they're bent, they're probably going to break. So there's kind of what you're saying in there, but yeah, an exact analysis, we should work on that.
Okay, but you did consider the, I guess, the structural strength of your glass mirror mounted at effectively a single point behind it?
Yeah, we basically talked about how the mirror itself and how much curvature can it take before fading.
Okay, because that again, that seems like a structurally inefficient design.
Definitely, yes. Thank you for your feedback.
All right, I'll let somebody else go.
Yeah, I'm gonna kind of pull on that same thread that Tom's talking to. So why just plain glass? Like I've seen several different designs that choose to use like a film. What was the trade study y'all did in order to choose glass over potential other options?
So we determined our glass based on the reflective area that it provided and the cost per meter squared. And the standard glass we found one that would that had like the lowest cost, and cost was what we all valued as the most important metric. And from that's where we took standard glass as our reflective surface.
Okay, and I will agree. That's one of the things that I did like on your presentation, was that you hit the $100 threshold, right? I do question your assembly and manufacturing costs. Could you talk a little bit to how you reach those? That they just seem low compared to what I would expect for your particular design here.
So the total cost to prototype one heliostat we found to be $24, and our assembly cost was very low because most of our parts are off the shelf. So our pan and tilt sub-assembly is off the shelf. And to produce one module, which is 4 heliostats, we got an assembly cost of $5, so just multiplying by 4. And most of our, since our goal was modularity, that this is like why our assembly time is so low, because most of our parts are off the shelf.
Okay. And then one of my final question. So you did this hole in the bottom of, or it's just a little bit above the ground, right? That your wiring is going to run through, and that's why y'all did the wind analysis, right? What is protecting the wiring that's going into the hole from environmental degradation over time? Because if wind is allowed to get in that hole with the wiring, I would think, you know, you have again, Nevada doesn't have huge rainstorms, but when you have a good rainstorm in Nevada, it seems like you would have the potential that you could have the water reach up and enter that hole, cause some corrosion from the inside out.
So I think the material of the pipe is the outside material of the pipe is the exact same as the inside material of the pipe. And we assume that if there were to be a heavy rainfall, the water would exit from the same hole that it enters through. The cap on the top, which houses the control subsystem, is adhesive, and we made sure that it was water resistant going up so that it wouldn't enter like the control subassembly such as the AC/DC converter and the controller. So it's protected from the elements in that sense. But the inside of the pipe, that's exposed.
Okay, yeah, I would be concerned over time that you're going to have some sort of pooling that occurs in the bottom of the pipe that's going to cause you issues and become a maintenance nightmare, in my own personal opinion. But I guess have to see how it actually performed out in the field. Good presentation, guys. Thanks.
Thank you for your feedback.
And we'll definitely look into the corrosion of the pipe, and we'll see if there could be a shielding feature that we could apply like in future research, basically.
Yeah, I'd specifically look at it buried in the ground, right? And that, I mean, bury chain link fence posts in the ground, but I don't know how long they tend to last. 20 years in soil could maybe be a concern with galvanized.
We found that the corrosion resistance for galvanized steel with a relative humidity of 50% was about 34 years. So that's kind of how we justified our lifetime in that respect.
Okay, was that out in the open? Because soil chemistry tends to do weird things with materials.
This was a number cited from a study, so it was not, I believe, for a post underground. So that would be something we have to look into.
Okay, we've got about 2.5 minutes before we hit that 45-minute mark. So if there are other questions from the
Sure. Fred Pendon, Carrier Corporation. I mean, I second Tom's concern with the single point attachment to the mirror. There probably could have been some better design choices to take up some of that moment that we're getting from the wind there. I do have another question though. The cleaning of these mirrors. Did you consider the access for a cleaning vehicle to each heliostat?
Yeah, so each module is going to have 8 foot of spacing and be placed in that row kind of radial staggered pattern. So we did that 8 foot based on the width of a truck, and that's how we determined what the spacing would be.
And that's a straight line 8 foot, or is it a zigzag?
So it's
No, that would align radially from the tower towards the outside.
Okay. Okay, good. Thank you. Yeah, no, that's all the questions I had. I think it's a great presentation. Thank you.
Thank you so much.
Thank you.
Okay, so we got like 1 minute left. So if there's a quick 1 minute question, we can entertain that.
If nobody's got a question, I'll just say I put it in the chat, but I'll say it out loud. I really appreciate you guys not using FEMs to show parts good here. This is a simple design, and everybody that's had a FEM for one of these, I've maybe over savaged, and you guys didn't, and I appreciate that.
Thank you so much. Really appreciate your
I
feedback.
appreciate
with
you all
everything.
coming. Yep.
All right, very good. Okay, so with that, then let's wrap up this session because we do have one more after this one, and we got a little bit of a late start, so maybe we can catch up a little more time. So let me drop into chat here. That's the Zoom link for our panelists for the next oral presentation. And with that, we'll wrap up. Thanks Group 1 for a great presentation, sharing your design ideas with us. And I'm going to stop recording.